Hello students, today's topic is colligative properties. So first question arises, what are colligative properties? The properties of the solutions which depend only on the number of solute particles but not on the nature of the solute are called colligative properties. These are also called democratic properties because just as in democracy or in elections, it is only the number of persons or the number of votes which counts, irrespective of the nature of the person. That is why these properties are also called democratic properties. These are of four types. First is relative lowering in vapor pressure. Second is elevation in boiling point. Third is depression in freezing point. And fourth is osmotic pressure. So in this video, we are going to discuss first two colligative properties. So the colligative properties are those which only depend upon the number of solute particles, but not on the nature of solute. So our first colligative property is relative lowering in vapor pressure. As we discussed earlier, that when a non-volatile solute is added to a solvent, the vapor pressure of the solution decreases. This is because non-volatile solute does not contribute to the vapor pressure of solution because their molecules cannot go into the vapor state. Therefore, the vapor pressure of solution, that is P, will be equal to the vapor pressure of solvent only, that is of PA. Thus, P is equal to PA, that is the total pressure of solution is only due to the vapor pressure of solvent. But according to Rod's law, PA is equal to PA naught into XA. Therefore, P is also equal to P naught A into XA. This is because P is equal to PA, where XA is the mole fraction of solvent, XB is the mole fraction of solute, P naught A is the vapor pressure of pure solvent. Since XA is always less than 1, thus the total vapor pressure of solution is always less than that of pure solvent, that is P naught A. Rearranging the above equation, P upon PA naught is equal to XA. Subtracting each side of the equation from 1, we have 1 minus P upon PA naught is equal to 1 minus XA. As already done, P naught A minus P upon PA naught is equal to XB. That is equation number 1. This is because XA plus XB is equal to 1 or 1 minus XA is equal to XB. So we put XB instead of 1 minus XA. Thus, relative lowering in vapor pressure of an ideal solution containing non-volatile solute is equal to the mole fraction of solute at a given temperature. So according to equation number 1, the relative lowering in vapor pressure only depends upon the molar concentration of solute, that is the mole fraction. Thus, it is a colligative property. So by studying the colligative properties, we can determine the molecular mass of an unknown solute. So let's discuss how we can determine the molecular mass of an unknown solute with the help of lowering in vapor pressure. So according to Rod's law, relative lowering in vapor pressure for a non-volatile solute is P naught A minus P upon PA naught, that is the relative lowering in vapor pressure, is equal to the mole fraction of solute, XB. Suppose WA and WB are the weights of solvent and solute respectively. MA and capital MB are their respective molar masses. So always remember, we write capital A for solvent and capital B for solute. Then mole fraction of solute XB is equal to number of moles of solute divided by total number of moles of all the components, that is solute and solvent, where Na and Nb are the number of moles of solvent and solute respectively. So, number of moles of solvent Na is equal to weight of solvent, that is Wa, divided by molecular weight, Ma. Similarly, number of moles of solute B is Nb is equal to weight of solute Wb divided by molecular weight, capital Mb. By putting the values of Na and Nb in the formula of mole fraction, we have Xb is equal to Wb upon Mb divided by Wa upon Ma plus Wb upon Mb. Let it be equation number second. Since for a dilute solutions, number of moles of solute, that is Nb, is very smaller as compared to the number of moles of solvent, or we can say that Wb upon Mb is very small than Wa upon Ma. So we can write the above equation number second as Xb is equal to Wb upon Mb divided by Wa upon Ma. So here in denominator we can neglect the number of moles of solute, or is equal to Wb into Ma upon Mb into Wa. So substitute the value of Xb in equation number first, which is the equation of relative lowering in vapor pressure. So we get Wb into Ma divided by Mb into Wa is equal to relative lowering in vapor pressure, that is Pa0 minus P upon Pa0. So from here we can easily determine the molecular weight of solute Mb by rearranging this formula. So let's try one numerical, that the vapor pressure of ethanol and methanol is 44.5 and 88.7 mm of mercury respectively. An ideal solution is formed at the same temperature by mixing 60 gram of ethanol and 40 gram of methanol. Calculate the total vapor pressure of the solution and the mole fraction of the methanol in the vapor phase. So from the statement, it is clear that the solution is formed by two components, that is ethanol and methanol. Both are volatile. They can go into the vapor phase. So let's try some back calculations, that to calculate the total vapor pressure we have to find out the pressure of the two components, because the total vapor pressure P is equal to pressure of ethanol plus the pressure of methanol. So how we can find out the pressure of ethanol? By applying Rod's law, that is P ethanol is equal to P naught A into XA. P naught A is the vapor pressure of pure ethanol and XA is the mole fraction of ethanol. So in this statement, vapor pressure of pure ethanol is given to us. So we have to find out the mole fraction. So to find out the mole fraction, we have to find out number of moles of ethanol. Similarly for methanol. So let's start the calculations. So first we have to write what is given to us, that is vapor pressure of pure ethanol, Pa0 is given to us, that is 44.5 mm of mercury. Vapor pressure of pure methanol, Pb0, that is equal to 88.7 mm of mercury. Weight of ethanol, Wa is given, that is 60 gram, and its molecular mass, capital Ma, that comes out to be 46 gram per mole. By putting the values of respective carbon, hydrogen and oxygen molecular weights. The weight of methanol Wb is equal to 40 grams, and its molecular mass we can find by putting the values of respective carbon, hydrogen and oxygen. It comes out to be 32 gram per mole. So the number of moles of ethanol Na is equal to weight of ethanol divided by molecular weight. 60 divided by 46, that comes out to be 1.304. And number of moles of methanol Nb, that is equal to Wb upon Mb, is equal to 40 divided by 32. It comes out to be 1.250. So from the values of number of moles, we can find out the mole fraction of ethanol Xa is equal to, that is number of moles of ethanol divided by total number of moles of both the components. By putting these values, it comes out to be 0.51. And the mole fraction of methanol we can find out by applying formula Xb is equal to 1 minus Xa, that is equal to 1 minus 0.51, it is equal to 0.49. So according to Raoult's law, P ethanol, the partial pressure of ethanol, is equal to the product of the vapor pressure of pure ethanol and its mole fraction, which is equal to 44.5 into 0.51. That comes out to be 22.69 mm of mercury. And P methanol is equal to Pb naught into Xb. And by putting these values, it comes out to be 43.46 mm of mercury. So from the pressure of both the components, now we have to find out the total vapor pressure. P is equal to Pa plus Pb. By putting the values of both the vapor pressures, that comes out to be 66.15 mm of mercury. So now we can find out the mole fraction of methanol in vapor phase by applying formula P methanol divided by total vapor pressure. So pressure of methanol is 43.46 mm of mercury divided by total vapor pressure, that is 66.15. It comes out to be 0.657. Let's try one numerical based on the colligative property relative low vapor pressure. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolytic solid weighing 0.50 gram is added to 39 gram of benzene, whose molar mass is 78 gram per mole. So the molar mass of benzene is given, that is 78 gram per mole. The vapor pressure of solution is 0.845 bar. What is the molar mass of solid substance? So in this numerical, the solvent is pure benzene and the solute is a non-volatile unknown solid. So let's start the calculations. So the vapor pressure of pure benzene, Pa naught, is given to us, which is 0.850 bar. Vapor pressure of solution after mixing, P is equal to 0.845 bar. Of solvent benzene, Wa, is also given 39 gram. Weight of solute, it is equal to 0.50 gram, which is also given. Molecular mass of benzene is also given, that is 78 gram per mole. So by applying the formula of relative lowering in vapor pressure, that is Pa naught minus P upon Pa naught is equal to Xb, or we can write as it is equal to Wb into Ma divided by Mb into Wa for very dilute solutions we have discussed earlier. So by putting these values, Pa naught is 0.8, P, that is the pressure of solution, 0.845 divided by 0.850, it is equal to Wb, that is 0.5, into Ma, that is 78, the molecular mass of benzene, divided by, which we have to find out, into 39, that is the weight of solvent. So it can be written as 0.005 divided by 0.850. It is equal to 0.5 into 78 divided by mb into 39. So by rearranging the equation, mb can be calculated as 0.5 into 78 into 0.850 divided by 0.005 into 39, which comes out to be 170 gram per mole. So our second colligative property is elevation in boiling point, which is related to the first colligative property, that is relative lowering in vapor pressure. So before going to start, let's understand what is boiling point. So in lower classes, we can say that boiling point is the temperature at which the water or any liquid boils. But in higher classes, this definition is not sufficient. So the boiling point of a liquid is the temperature at which its vapor pressure becomes equal to atmospheric pressure. As we already discussed, that as vapor pressure of solution containing non-volatile solute is always less than that of pure solvent. So if we add a non-volatile solute in a solvent, the vapor pressure of the solution decreases. So if the vapor pressure of solution is less, then therefore the solution has to be heated to higher temperature so that its vapor pressure becomes equal to atmospheric pressure. Thus the boiling point of solution is always higher than that of pure solvent. So if we plot a graph between vapor pressure and temperature, we take temperature along the horizontal line and vapor pressure along the vertical line. The yellow curve shows the variation of vapor pressure of solvent with temperature. As the temperature increases, the vapor pressure of solvent increases from point A to point B. So now, if we add a non-volatile solute in a solvent, the vapor pressure decreases. So the variation of vapor pressure of solution with temperature is shown by red line, which is less than that of vapor pressure of the solvent. Now draw an imaginary line represents the atmospheric pressure, which is 1 atmosphere. It cut the two curves, that is a yellow and red curve, at points X and Y. So corresponding to point X, the temperature is the boiling point of solvent, TB naught, and corresponding to point Y, which shows the boiling point of solution, it is TB. So it is clear that the boiling point of solution TB is higher than that of solvent TB naught. So the difference between the boiling point of solution TB and pure solvent TB naught is called the elevation in boiling point, delta TB. Mathematically, delta TB is equal to TB minus TB naught. Let it be equation number 1. The elevation in boiling point delta TB of a solution is proportional to the molar concentration of the solution. That means delta TB is proportional to molality, small m, or delta TB is equal to Kb into m. Let it be equation number second, where small m is the molality of the solution and Kb is the molar boiling point elevation constant or ebullioscopic constant. If the molality of a solution is unity, then delta Tb is equal to Kb. Thus, we can define the Kb as the elevation in boiling point for 1 molar solution, that is a solution containing 1 gram moles of solute dissolved in 1000 gram of the solvent. As elevation in boiling point is directly proportional to the molar concentration of the solute, and therefore it is a colligative property. So from elevation in boiling point colligative property, let's determine the molar mass of solute. Let Wb gram of non-volatile solute is dissolved in Wa gram of solvent, and capital Mb is the molar mass of solute. Therefore, small m, that is molality of solution, is moles of solute divided by weight of solvent in grams multiplied by 1000. Moles of solute, Nb is equal to weight of solute divided by molecular weight. So the formula comes out to be small m is equal to Wb upon Mb into Wa multiplied by 1000. Substituting the value of molality in equation second, that is delta Tb is equal to Kb into m. So substitute the value of m in that equation. So we get delta Tb is equal to Kb into Wb upon Mb into Wa multiplied by 1000. By rearranging the above equation, we can easily determine the molecular weight of solute, capital Mb, as Kb into Wb divided by delta Tb into Wa multiplied by 1000. Let it be equation number third. So let's try one numerical based on elevation in boiling point, colligative property. The numerical is 18 gram of glucose, whose molecular formula is C6H12O6, is dissolved in 1 kilogram of water in a saucepan. At what temperature will the solution boil? The Kb for water is 0.52 Kelvin kilogram per mole and boiling point of water is 373.15 Kelvin. So in this numerical, solute is glucose and the solvent is water. So let's see what is given to us. The boiling point of solvent, that is water, that is given 373.15 Kelvin. The boiling point of solution we have to find out, that is we have to find out Tb. Weight of solute, that is the weight of glucose, Wb is 18 gram. Weight of solvent, Wa is 1 kilogram, or it is equal to 1000 gram. The molecular mass of solute, that is glucose, is 180 gram per mole. So by applying the formula of elevation and boiling point as delta Tb is equal to Kb into m, where m is the molality of the solution, so we can write as delta Tb is equal to Kb into Wb upon Mb into Wa multiplied by 1000. So by putting the respective values, that is Kb is 0.52 into Wb is 18 into 1000 divided by Mb is 180 into Wa, that is the weight of solvent, that is 1000 gram. So it comes out to be 0.052 Kelvin. So now the elevation and boiling point delta Tb is equal to Tb minus Tb naught. So from here Tb can be calculated. Tb is equal to Tb naught plus delta Tb, which comes out to be 373.15 plus 0.052 Kelvin. That comes out to be 373.202 Kelvin, which is the required answer. Let's try another numerical related to elevation and boiling point, which is the boiling point of benzene is 353.23 Kelvin when 1.80 gram of non-volatile solute was dissolved in 90 gram of benzene, the boiling point is raised to 354.11 Kelvin. Calculate the molecular mass of the solute. Here, the Kb for benzene is given 2.53 Kelvin kilogram per mole. So in this numerical, the solvent is benzene and the solute is an unknown solid whose molecular mass we have to find out. So let's see what is given to us. That is the boiling point of solvent benzene Tb naught is 353.23 Kelvin. The boiling point of solution Tb is also given 354.11 Kelvin. So the elevation in boiling point delta Tb, which is Tb minus Tb naught, which comes out to be 0.88 Kelvin. So weight of solute is given 1.8 gram, weight of solvent 90 gram, Kb for benzene is 2.53 Kelvin kilogram per mole. So by applying the formula of elevation in boiling point and rearranging it to find out the molecular mass of a solute as Mb is equal to Kb into Wb upon delta Tb into Wa multiplied by 1000. So by putting the respective values, which are 2.53 into 1.80 into 1000 divided by 0.88 into 90, which comes out to be 57.5 gram per mole. So in our next video, we will discuss the rest of the two colligative properties. So please subscribe my channel and click the bell icon for further updates. Thanks for watching.